Hello everybody, Chris Evie Jackson here. Oh, a blank screen. Look, here we are. Right, I'm going to go back to Google at the moment. Here we are. Today is Gottfried Wilhelm Leibniz's 372nd birthday. Well, I saw this earlier on and I thought, oh yes, who is that? So I read a bit about him. Yeah, interesting chap. Born in the 1600s. And he was a mathematician, philosopher, and yeah, it was quite a good read. He was responsible for doing some work on calculus, or coming up with the derivatives for calculus, and he was accused of plagiarising Newton, who was most upset by this chap. But nevertheless, as time marches on, it's been proven some of his unpublished work that he did in fact do a lot of work with calculus, come up with similar constraints as such as Newton, but a lot of his work has now been taken as the forerunner to the calculus, and he's the chap that actually came up with the elongated S, which denotes the calculus limitations and of the derivatives. So yeah, so I watched Martin Leaker's video today, and thanks for the mention, Martin. Appreciate it. About the plane. But there you did briefly mention this as well, so I thought, oh yes, of course, I remembered. So I thought that sparked me to think that maybe there's a hidden code within this binary system here. He was responsible for dealing with some systematic logical approaches to stuff, as well as his philosophical approaches. And George Boole, who was the forerunner of the Boolean algebra, came up with this. So by looking at this, I just wanted to run through it, and I thought I'd just use my sketch pad for a bit of fun, and just going to get this other thing out of the way and then bring it up. So right, so first of all, go back to here. So please make a note of this, if you like, what it says along the top here. Alright, so we've got 6 strings of 8 bits, right? Okay, now I just want to try and explain this as easy as I can. Now the first line, I'm going to use my pen here. Let's try that. Let's go here. Is it? It's not coming on now. Why is it not coming on? Come on. Typical. Right, here we are. So the first string was 0, 1, 0, 0, and the accompanying one was 0, 1, 1, 1. Now, sorry, it's a bit. No, what happens with this is if I separate those two out here. Now, computer languages, as we all know, it's all transparent to us. We don't deal in ones and zeros, as it did would be very laborious. So the computer at the base level is dealing with ones and zeros and all its permutations and its calculations. But when we type something, everything gets converted. So everything gets converted from computer language down into code, and that code becomes ultimately ones and zeros, which is spanned about throughout the computer and calculated as such. But when it kicks out information, sometimes from computers we get results. It deals with blocks of information, if you like, and so this is binary, which technically is either a 1 state or a 0 state, as we all know that. So it's denoted by, you could write that down as 10 to the 2, to the base 2, which means it only has 2 states. So there's 0 units and 1, 2. Okay, so that would be, so you'd have a 1, 1 there. That would be half 2, so it would be a 1. But a 1 in this position would denote 2. Now let me explain that. We're used to seeing this, aren't we? When we write this, okay, we know it's 10. I have 10 of something. But if I had to write this similar to this number here, that's to the base 2. This is to the base 10. So I would write a 10 here, right? But we don't write 10 to the 10 because that would be quite laborious. Any decimal number, decimal again, 10, is denoted, we don't denote it to the base 10 because we know it's 10, right? We go to school and we think in decimal terms all the time, which means I have no units and I have a 1 10. A 1 here would be I have 1 in 100, so that's 110 and no units. But let's get rid of this one because we don't need that 10 there. Let's get rid of that 100. Right. So in terms of computer languages, they tend to work in hexadecimal, and the reason why that is because the hexadecimal blocks are taken from the bytes. Now, as we all know, this would be called a bit. 4 bits, 1, 2, 3, 4, make up a byte. Actually, half a byte is 2 bits. It's called a nibble, but they never use that. But these are the terms. I didn't make this up. This is true. Anyway, so we talk in terms of bytes. We've all heard about gigabytes of memory, and we've all heard about, you know, the RAM and the size of the RAM. It's like, you know, 12 gigabyte RAM or whatever. It was a hard disk is so many bytes. Yeah, the size of it. So what that means is the gigabytes is if it's say like a 1 gigabyte, you've got 1,000 of these 4-bit locations, and it's given this could have a value. It'll actually be assigned a value. So this value at the moment is actually, believe it or not, is 7. Now why is that? Okay, I'm going to explain now. So the very left hand side, the right hand side, least significant bit, would be weighted as a 1, the next one as a 2, next one as a 4, and then this one as an 8. Alright, just give me a slide if I sound patronising. I don't mean to be. And this one also the same. 1, 2, 4, 8. Now this basically is a basic level of computer science, if you like. I mean, you probably taught this, I can't remember, GCSE maths or something. I don't know, just to get your head around this numbering system. So as I said, 10 to the 10. Now, when I said hexadecimal, what hexadecimal is 10 to the base 16. Now that makes it so I have 0 units and I have 1/16. So 11 to the base 16. If I had to convert that into decimal, 11 in hexadecimal is actually equal to 17 to the base 10 decimal, right? Because that means I have 1/16 and 1 spare unit, which is 17. I hope that's clear. Right, so over here, coming back to here then, bearing in mind I wanted to see if there was any secret coding into this binary pamphlet here that's supplied on Google, just for a bit of a laugh. We can oh good, I'm still recording. That's good, because before it stops. Right, anyway, so with this then, this actually comes out to a value of 4 and then 7. Because basically where these bits are, I'm adding them up for the weighting. So it's 1 plus 2 plus 4 is 7. And I've only got 1 4, so it's a 47. But don't forget, that's to the base 16. Right, okay, now my phone's going. Excuse me. I'm just going to silence that down a bit. Right, so the next number in the configuration was 0 1 1 0, blue bar, let's say, and then it's 1 1 1. And the only reason why I'm separating these out, even though they are a complete string here, as I said, I have to break these down because the hexadecimal would actually be deals with bytes. So I could say 1 2 4 8 16 32, which wouldn't yeah, okay, necessarily be quite correct. I need to break them down into configuration of words. So back to here, and that this one here actually turns out to be 6F. Alright, now why F? Where do I get the F from? Well, now let's go back to here to the 10 to the base 16. As we all know, for 10 in decimal numbers, 10 to the base 10, I have 110 in new units. So I go from 0 to 9, yeah, and then I have to go to 10. So I go 1 2 3 4 5 6 7 8 9 10. This number, this actually here is 10 values, yeah, because 0 is a value. If I counted one value at 0, so between 0 and 9 is actually 10. So the transition over to 10 would equal, yeah, 1, 10 and 0 units, but we have to go from 0 to 9 first before we get 10. Now to the base 16, I've got to get to 15 before I have 116, right? So the way they do that is they actually denote 10, instead of writing 10, because we can't, because 10 to the base 10 is 10, it's 110. But we don't want to denote 10, we want to denote 16, A16s. So what they term is they go from 10 is A, 11 is B, 12 is C, 13 is E, 14 is D, A, B, C. Sorry, I got that wrong. Hang on a sec. My phone's going crazy. Sorry, can't get my alphabet right. Hang on a sec. No, put that back. Dear, I'm a silly billy. Right, sorry. Start again. My phone's going a bit funny. Come back here. Right, so A, B, C, D. A, B, C. Maybe if I said the tune it would have been better. A, B, C, D, E, F. So that's 10, 11, 12, 13, 14, and there we go, 15. Alright, so it's 15. So F is 15, because we go from 0 to 15 the same way as we went 0 to 9, and then 10 to 0 to 15, and then we have a 116 and 0 units. So do not that to 1016. Right, and so 116 and 1 unit is 17, because we still use decimal numbers between 0 and 9 even in hexadecimal. It's just that when we get to 10 we denote it by A, B, C, D, E, F. Normally when you get a new programmable device, if you looked at all the locations, you'll see that all F, because they're all set to 1. So that's F. So this value here, which is the second part of the I'm going down, by the way, on from top to bottom, is 6F, and then the next line down, 6F also. Let's jump back to the web page. So there's my 6, there's my F, there's my go away, there's my 6, and there's my F. And now onto these 3 lines here. Well, to save you the laborious save me the laborious task of going through them, I'll write them out here. And so I just put them all in order here. So instead of writing down 47, I'm just explaining why I went to, and then this one was 6F, 6F. You can work the others out if you like, but just to save argument, it was 6, 8, 6, 8, 6. Oh, did I say 8 again? Oh, I didn't mean 8. I'm terrible. 6, 8, not 6, 8. It's 6C. What am I like, people? Come on. Trying to use this pen. 6C. Because that value is 1100, and that's 12, which comes down to here, 6C, you see. And then the last but not least is 6.5. So that represents 4768 here, 4768, 4768, 6F, 6C, 6F, 6.5. If I put this, had this, that's what it would actually come out to in hexadecimal, because it's easier to deal with hexadecimal than reading binary. Okay, oh, what is that equal to? I don't know. So you write it in hexadecimal, which is to the base 16. So I know I've got 4 16s and 7 units. So that would be 40 multiplied 4 16s, that's 64, 71. So 47 to the 16 is 71 decimal. And there we have it. But now what I was looking at was I was trying to find if there was a code here somewhere. The only thing that stands out is 666. Well, I don't think that's really that hidden. I'd also equated the weighting of the numbers 4, 7, 6, 8 into the 26 letter alphabet. I came up with 5 F's, 2 O's, 1 D, G, H, L and E. Put that into an anagram generator, and it just didn't give me anything. So play with these what you will, if you like. Here they are, they're the numbers. I just thought it would be a bit of fun. You never know, I might have found something, or there could be something in this which could be attributed to some code that I don't know about, or try finding something referencing 4768 type it into Google, perhaps have a look and see what, I don't know, it might be equated to something that I haven't found yet, but I just thought I'd do this for a bit of fun. Okay, everybody, well, again, happy 372nd birthday, Gottfried Wilhelm Leibiniz, and quite a contributor to mathematics, philosophy, and the like. Good chap. Thank you very much. Goodbye.